We are back again with the combustion monitor. In this part, we will check the adjacency alarm. Thermocouples are installed. Consider them in a ring from number 0 to number 12, and we have several adjacency scenarios. For example, number 1 and number 2, they are adjacent. Number 2 and 3, 3 and 4, 4 and 5, 6 and 7, 8 and 7 and 8, 8 and 9, 9 and 10, 10 and 11, 11 and 12, and 12 and 0. That's a big issue. 0 and 12, they are adjacent. In order to find out if two adjacent signals are less than low alarm, we need to treat adjacency in position 0 and position 12 differently. And the rest of the, these are the boundary conditions, position 0 and position 12, because they are in physics, they are in actual installation adjacent, but in the math, in the arithmetic, we don't consider 0 and 12 to be adjacent naturally. So we need to do the some exceptions here. We need to treat thermocouple number 0 and thermocouple number 12 differently. We need to treat them differently because they are adjacent in this example. It's a ring of thermocouples. So it's very similar to the ordinary alarm check, but we have a for loop here. It's a very complex for loop, but if you understand the adjacency and how to program adjacency, you are professional. You're getting professional in SCL programming. So first we check the if I is 0. If I is 0, so we need to check the adjacency for 0 and 1 and 0 and 12, because 0 and 12, they are adjacent based on installation. So if thermocouple number 0 is less than low alarm, if thermocouple number 1 is less than low alarm, this is the AND logic, or thermocouple number 0 is less than alarm and 12 less than low alarm. In position 0, if one of these conditions are met, we have adjacency alarm in position 0 and we exit the whole for loop here. This is important. It's important exit here. So if I is 0 and one of these conditions are met, we have the adjacency alarm in position 0. Otherwise, I can be 12. For I 12, we check if position 12 and 11 if they are less than alarm, or position 0 and 12 if they are less than alarm, and we generate the signal exit. If I is not 0 and if I is not 12, it's in the middle. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So these are not boundaries. They are in middle. So the condition in middle is somehow similar. We check if the current position, if it's I, consider I is 5, if thermocouple 5 and 6 less than the alarm, or thermocouple 5 and 4, the adjacent thermocouples. Because they are not boundary, they are not in the boundary conditions, and we can check the adjacency by eye, by the loop counter. If we want to use this formula for whole conditions, even for boundaries, PLC will not be happy with the thermocouple position -1, or in 12 it's not happy with the thermocouple number 13, because they are not existing. Because it's a loop, we need to treat the adjacency in boundaries differently, and in the rest of the thermocouples we need to use this formula. So if we have at least one of the adjacency true, we generate alarm and exit, and if none of them is true, we make the adjacency signal 0, and that's finished. This is for adjacency alarm. For adjacent trip, it's very similar. We treat the boundaries different. We simply just check the low trip signal. Very similar. Here we enable the trip and we exit. If I is equal to 12, check the boundaries here. Similar. Enable the trip, and if it's in the middle and it's not in boundary, similar to previous, we only just change the limit here. If we are less than the low trip signal, we enable the adjacent trip signal and we exit this loop. Adjacent trip signal is checked for validity for 5 seconds, and if it's active for 5 seconds, this signal is activated, and by using this structure we latch S prior flip-flop. If we have the signal, reset is not working. If the signal is gone, it's possible to reset the trip signal. It's somehow a complex algorithm for combustion monitor. It's a pure calculation, array manipulation, and we use some of the function blocks that we developed in the previous lessons, and we just assembled our thoughts, and this is somehow similar to actual program that is working in a real industrial gas turbine. So we stop the video here, and the last topic will be function test the block. We will function test, and that will be the end of this topic.